to provide a forum for promoting knowledge sharing and collaboration in the realm of environmental remediation. Before I get into today's seminar, I just want to say, if you follow RemPlex activities, you'll know we've had a bit of a hiatus since our global summit last November, and we're pleased to be kicking off our 2022 program. Before everybody slips away from us, I just want to put in a plug that our next seminar after today will be scheduled for late April, and we're going to focus on the topic of climate change and climate resiliency planning related to remediation. I will put a link to the RemPlex website in the chat here in a minute, and at that website you can get more information about RemPlex, and you can get information about past events such as recordings of previous seminars, as well as all the materials related to the summit last November. For your information, this seminar is being recorded, and this recording will be made available on our website in the future. We'd like to ask that you keep your microphone on mute during the presentation. Today's seminar is a presentation on TCE remediation work at Joint Base Lewis-McChord, which is located just southwest of Tacoma, Washington. And our speakers are Christian Johnson and Dr. Michael Annable. Chris is sorry, I just lost my notes. There we go. Chris is a senior development engineer at PNNL's Earth Systems Science Division, and he conducts research and development in the field of environmental remediation, covering a broad spectrum of issues for a very diverse set of clients. Mike is a professor at the University of Florida, and he's the head of the Department of Environmental Engineering Sciences. His research interests focus on the development and application of innovative technologies for subsurface remediation and characterizing hydrologic systems. We're going to have a Q&A session after the presentation, so please submit your questions and comments for our speakers in the chat tool. And with that, I'm going to turn it over to Mike and Chris.
Great, thanks, Karen.
Sure.
So Mike and I are going to talk today about a case study at Joint Base Lewis-McChord to describe some strategic monitoring approaches and remedies for source removal and control, where again, the challenge was trichloroethene NAPL in a source area and a large dissolved phase groundwater plume in complex geology. And the approach that was taken was multiple remedy elements to address both the source and the dissolved phase plume, and using mass flux to help determine source strength, guide remedy design, and provide some performance monitoring. So all this came together to help verify the thermal treatment performance in the source area. There was pump and treat, source control implemented, and both of those actions really helped decrease the overall remedy duration. So as we talk today, I'm going to go through we'll go through several things here. I'll introduce Joint Base Lewis-McChord, talk about the site and characteristics. Mike's going to talk about mass flux for remedy performance monitoring, and then I'll come back and talk about the pump and treat that was applied for source control. So Joint Base Lewis-McChord is formerly known as Fort Lewis. They have a logistics center area that had contaminated groundwater. It was TCE, trichloroethene, that was historically used as a degreaser or a solvent in equipment maintenance, and they disposed of waste solvent in drums and put it in landfill 2, which was also known as Eastgate Disposal Yard. So remedial investigations began in the 1980s and have continued in terms of characterization. In terms of regulatory landmarks, the site was put on the National Priorities List for Superfund in 1989 with a record of decision for pump and treat in 1990, and then a later explanation of significant difference in 2001 that addressed source area treatment. And if you want to see more details, there's a remedial action completion report that EPA put out that has a lot of this history as well. So here's an overview of the site, just a plan view. We've got Interstate 5 runs diagonally up across the site, the image here. Landfill 2 is off to the east here, and that was the source area that generated this dissolved phase TCE plume that migrates down gradient towards American Lake. It turns out that there's actually, and this is in the upper aquifer, and it turns out there's actually a window between this upper aquifer and a lower aquifer. And so TCE goes through that window down into the lower aquifer, which has different hydraulic conditions, and so you get a different flow direction, and it has a TCE plume as well. I'll give you another picture of this. Here's a 3D view of these plumes, again with the source area off on the right here. You see the TCE going down gradient in the upper aquifer, and then going through the window down the lower aquifer. There's actually 3 pump and treat systems here. One by the source area. There's one near Interstate 5 that helps prevent off-post migration. And then there's a pump and treat system in the lower aquifer to address that contamination. And we'll talk a little bit more later about the thermal treatment. There were 3 different NAPL areas in the source area that were dealt with thermal treatment. Here's a cross section to give you kind of an idea of the complexity of the geology. There's a mixture of higher permeability outwashes and low permeability tills and lacustrine sediments. Quite a range of different hydraulic conductivities. And here again is this window just down gradient of the lacustrine low permeability zone that allows the TCE to get into this lower aquifer. And this purple here is the aquitar between the 2 aquifers. And all this was represented in a numerical model that was used for both remedy assessment and design. I'm not going to get into details of the numerical model, but that was a key instrument to help with these assessments and design. So just a summary of the source area treatment. So this was assessed in after the ESD in 2001, and it was determined that treatment was really the only way to significantly reduce the source lifetime and overall cost. If we didn't do source treatment in landfill 2, the pump and treat would need to continue for about 500 years. So obviously that's really impractical. So the remedial alternative assessment determined that thermal treatment was a preferred remedy. And so there was a particular cost for that, and that would expected to leave some residual contamination. So pump and treat would still be necessary, but on the order of a 40-year lifetime for that. And the overall source flux reduction was estimated to be about 95% with this action. So with that, I'm going to turn it over to Mike and let him talk about flux measurements and how those were useful.
Thanks, Chris. You can hear me all right, I assume?
Yes.
Yeah, this goes back a ways when we first started thinking about how to better characterize sites, maybe focusing on mass flux, maybe doing calculations on mass discharge, and that kind of ties into plume behavior, plume response, and that important linkage between those 2. And of course, if you do some source remediation and reduce mass flux, how does that improve your site, which is what Chris just mentioned. Next slide, please. So our conceptual model is pretty basic, where we've got a DNAPL as shown in the dark red area on the left, a DNAPL source area. There's a source control plane, downgrading of that source area, and then there's the dissolved plume that could extend for quite some distance, which it obviously does, as Chris just showed at Fort Lewis. So we're interested in kind of knowing the mass balance along these sections of the plume, and maybe more importantly, what can we do at the source area to reduce mass flux. Next slide. So conceptually, we imagine a control plane downgrading of the source, and in the case of this site, it was buried drums and trenches, but variable flux distribution across there that's driven by both concentration and groundwater flow. So low flow and moderate concentrations are probably not as significant as the high flow zones with high concentration. So we need to kind of understand that distribution, or at least know where the hotspots are. Better remediation, better understanding of our site conceptual model. And so we kind of set out with that as a goal in mind with our CERTIP funding that we had for both kind of understanding mass source behavior over time, and then also how do we measure these fluxes and mass discharge. Next slide. So we developed quite a while ago, this was published in 2004, I think, the concept of a passive flux meter that we insert into a well screen It's typically a granular activated carbon that has tracers embedded on it, and it is also absorbent for the contaminant of interest. And we've done lots of different organic contaminants and a number of inorganics as well. We put these in to the well screen. They're usually 5 feet long. In the case of the site today, I think there were 5 of them, 25 feet of passive flux meter installed in each of 10 wells. So it's 50 PFMs, a pretty big deployment back in 2003. Next slide. So we were looking around for sites and discovered the Joint Base Lewis-McChord site. And immediately they made it very clear to us that it was a very complex site. And we knew that by the plume and the source area size. And but we thought it was a good site to work at because it was so well characterized, and in particular in the source area, they were gearing up for thermal remediation. This was an opportunity to do pre and post assessment, and that was one of the things our project was aiming to do. And so in 2003, 2004, thermal remediation heated the site up near 97 degrees. So driving off, vaporizing TCE was the goal of that technology. So lucky for us, we were able to squeeze in there before they started the thermal and do our measurement along a control plane, downgrading of this sizable source zone. And a lot of this work was done with Linwood and Mike Brooks and Carl Enfield as well at EPA Lab, Oklahoma. Next slide. So this is a little bit cruder picture than what Chris showed, but conceptually the same. There's the source area back on the lower right-hand side that we're going to focus on in a minute. But this big plume has quite a bit of data, and I'm not going to go into that, but Chris did mention the I-5 pump and treat at the lower end. So there's another kind of a flux mass discharge point, and then also the work that's going on in the lower Vashon. So yes, complicated, but without question, we need to go back to that source area and reduce the load coming out of there. Otherwise, we're looking at that 500-year mark. Next slide. So back here, we're in the source area, much smaller scale than what we just looked at. And in the green highlights are 3 areas that were identified as heavily contaminated and in need of source remediation. Next slide. These sites were identified by an extensive characterization effort and identifying where trenches and buried drums were, and a lot of that mass was removed. It's probably unknown quantities of DNAPL that were removed from the site, but in the end there were very clear 3 areas, 1, 2, and 3, that were remaining high DNAPL residual, TCE primarily. But I will kind of point out a little bit to the, I guess it'd be east of area 3, that kind of lobe of 100 up there. Later on, there was found to be some levels, not nearly as high as the other 3. So those are the dominant source areas, and those were those targeted for thermal treatment. Once you do that, you know, it's not uncommon that the next hottest spot becomes the new hotspot in their source area. But so we're going to go to area 1. Next slide. I guess there's just this last slide. This does allow us to point out there is a pump and treat system, which Chris referred to, and it makes kind of a upside down J around all 3 of these sites, and that's critical piece of information for long-term performance assessment of the remedial action that's done in the NAPL areas. So I think the next slide, let's go to area 1 specifically. This is the area. It's still a rather large area. There's I believe it was 105 or so heating electrodes that were used for the resistive heating portion of this, and of course vapor extraction and treatment and system. It's pretty high-tech remedial effort done by TRS back in 2003, 2004. But there's also this line of wells vertically on the left-hand side that is our 10-well transect. We were able to get in there and put those wells in with help from EPA ADA Lab. So we have a 10-well transect. and 25 foot vertically. And so that's a very nice control plane data set that we can get from our PFM deployments in that area. Next slide. So before thermal remediation, we map out the distribution of TC flux in this control plane. So we're now sitting in the source area looking down gradient, and the flux is in milligrams per centimeters squared per hour, which will integrate that to about 0.75 kilograms per day. So those are numbers that be nice if we knew for all sites, but it starts to put a site in perspective just a little bit. We worked at a dry cleaner site in Jacksonville, Florida, and the mass flux was about 1 gram a day. This here is 750 grams a day. There's another site in Hill Air Force Base where it was around 100 grams a day. So these sites vary according to how much mass is there, how it's distributed, what the flow of groundwater is like. And but that's a good way to compare sites and kind of categorize as well. So we're looking at 750 grams a day or so coming through that control plane. You will notice that the DCE control plane is a little different. There's a bit of a DC source. Well, it probably was originally a TC source that is converted to DCE, kind of on the right-hand side of the transect. But the main TC flux, which you can see is 750 versus 150 grams per day, is located in that region about 100 to 140 feet on the horizontal. Next slide. So the slide on the left is the Lewis-McChord remedial action. The red is the pre-remediation, and the blue is the post-remediation. Now it's very important to point out that the left and right axes on here are an order of magnitude difference. And so while that looks like an impressive reduction, you need one more order of magnitude difference between those two. So that turned out to be a bit higher than 98% mass flux removal or mass discharge removal from the site. We were extremely impressed with that. Thermal has always argued that it's very effective if done properly and you don't miss parts of the plume, and seems to be the case here that it was pretty impressive. The other graph just quickly is the Hill Air Force Base scenario, and that was about a 90% mass reduction. Once again, the axes are order of magnitude difference, so don't be tricked by that. Next slide. That was published back in 2008, by the way. So one of the things that we kind of argued, I'm sure it's really caught on as we'd like, but the better scenario would have been to get a measurement like this, and here I'm just showing the TC flux distribution, and then target the remedial treatment, upgrading into that if we're doing a thermal remediation area. And we kind of feel like you could probably treat the area with maybe 40% of the original design. Now, I think it's always challenging to try to focus something to get that much cost savings out of it. But I think in any case, you could have reduced the overall remedial cost. So it was about $4 million. The flux measurements we made would have been about 2% of that. You can do the math on that. So cost benefit analysis, we'd argue there's some value in getting this kind of spatial distribution like we have at this particular site. Next slide. So we did, this is a little bit tricky side. You should start on the right-hand side. There's our source area, there's our control plane. The first control plane is the 2003 that we've been looking at already. The next one over is 2006. Now this is about 2.5 years after remediation, and like a lot of sites, when they finished thermal, immediately said, well, when are we going to go in and measure the flux? And we said, no, we have to wait for the site to cool down, first of all, and wait for the flow to kind of reestablish itself through the source area to the control plane. So that was the argument for waiting 2.5 years to get that. And it's very striking in the upper part of that hotspot is is completely removed. There's a little bit to the lower end of that transect. So then a few years back, sort of said we were interested in looking at sites that have been remediated for significant periods of time and look for rebound activity. So we put in a small proposal to go out and basically do the measurement again on the control plane that we have in place. I think we may have lost one well or so, but and so that 2018 is I guess you could say 15 years post thermal remediation, 14 or 15. And it really, if you compare the 2006 and the 2018, they're quite similar. And so we feel like there hasn't been a substantial rebound at all after 15 years. So it's a pretty good statement on thermal remediation of this sand and gravel type aquifer system. Next slide. So we come back to our conceptual model. We ask the question, if the source changes, source mass flux changes over time as a result of either aging of the source area or remediation, then we can use some type of a source strength model that we developed in, I can't quite see the numbers down at the bottom. There's about 1.5 kilograms and we estimate about 5,400 left. That's, if you just do the simple math, it'd take about 10 years to remove that. But of course, over time, the concentrations decline, and we had proposed a model there with a power law coefficient of 0.7. And we can use that to do kind of forward predictions like Chris was doing a bit earlier. Next slide. So there is a pump and treat that was put in north or down gradient of this source area. And all three treatment areas were completed by thermal remediation. We didn't look at the other ones as closely as we did at the first one, but assuming we're getting somewhere in that neighborhood of 98% reduction in flux from these source areas, then we should see that. And one place to look for that is at the pump and treat system. I believe that was initiated around 2007, and some of the data is shown there. I think go to the next slide. And so same concept, we can look at that declining concentration or mass discharge as a function of time and come up with some parameters. This is now a first order reaction rate and a post remedial mass estimate. Next slide. And we can take that and plot that data and the model together. And so we do have a decent record starting in 2007 to 2016. Once again, this is the pump and treat system removing mass, downgrading of those source areas that were treated. So when I look at this, I think that the first probably 3 or 4 years is reestablishing this new flow field with the pump and treat system and the substantially reduced source areas. And so we're seeing a nice decline in that. Now the model and the data deviate a little bit down at the lower right-hand end of the graph. Some pessimists might say, look, it's flatlined, but I feel like it's going to continue to migrate along that pathway. We need to go out and get that data, bring it up to speed for 2022 or at some point. Next slide. I think this is my summary for passing it back to Chris. And the argument is that this type of data can allow us to do mass flux and discharge calculations to do performance assessment on remediation, and then long-term predictions and behavior of contaminated complex sites like this. Chris?
Great, thanks. So yeah, that's Mike's covered the mass flux information. I'm going to go back and talk a little bit more about the landfill 2 pump and treat system for source control. So again, that's up in this area here. So and this will get into I'm going to just describe a little bit the history, and it really gets to how adaptive site management is important. You can't just pick a remedy and go with it, particularly at complex sites, because you'll get new information and need to adapt to that. So in this particular slide picture here, we're showing the initial site conceptual model had groundwater flow going down the axis of the plume in the direction of this red area to the northwest. So like you've seen in the previous picture with the TCE plume. And based on that, there was a 4-spot extraction well system that was at these pink dots that was installed in the 90s. And they put an infiltration gallery for treated water using air stripping. There's an air stripper system right here. So they take the treated water and put it into this infiltration gallery to the west here, nominally up gradient of the source area. So as more data was collected, it was determined that there's actually a seasonal hydraulic change in the upper aquifer, this Vashon aquifer, where the flow direction actually goes in the direction of this yellow arrow to the west certain times of the year, as the drainage to this local nearby stream here changes. And so, and they can see that in the hydraulic data as well as the TCE data. There's actually a lobe of TCE contamination that goes out to the west here. And that was something that wasn't initially understood, is the seasonal variation. So it was apparent, you know, the Annable thermal treatment did a great job, but we still needed to improve capture with this pump and treat system. So we used our numerical model to do some designs and prediction, and came up with a optimized system with 8 extraction wells in this V or dogleg format here that would capture both contamination going down gradients along the main axis, as well as protecting the western flow. And as part of this, we also moved the infiltration gallery down here to the south to help with the hydraulic control of that westward migration that occurs seasonally. So here you'll see the green lines are the hydraulic head contours, and then the blue lines are the pump and treat well extraction well capture. So this was designed to capture, as I said, flow to the west, and then in this crux of the V here, you got a significant hydraulic depression, so it would capture flow emanating out of the source area. So here's a couple of pictures showing the first 5 years of implementation of this redesigned pump and treat system. So in 2007, right after it was initiated, you see there's still high concentrations of residual TCE in the source area. The source control pump and treat is right in this area here. And then by 2012, you see a decrease, and you're starting to see detachment of the main TCE plume here from the source area. And that's really the objective, is the source control of controlling that mass flux out of the source area to reduce what's down gradient. And I'll show you, first I'll show you the capture. So this is some data over time on the different wells and what they captured. Again, here's a little picture of the wells here. And most of the TCE is captured by wells PW1 through PW5. PW 6, 7, 8 are a little more along the guard, sort of a guard wells for that particular end, that eventually those could probably be, you know, at least PW7, PW8 could probably be turned off. But most of it is being captured at this, the crux of the V along up here. And if we look at, again, so this is, some of this is actual data, some of this is predicted data. The time series plot here is at the I5 pump and treat system, which is this down gradient line right about here, near close to I5. And we have history matching data to say, well, what's going to happen. And this is when we implemented the pump and treat for source control. And then the numerical model predictions say, well, as time goes on, we're going to expect to see that really decline. And you can see it in the images below here, where you start out with a pretty high dissolved phase plume in the upper aquifer, and then that eventually decreases as it tails off, because we're controlling that source. We tail off, and then here's 20 years later, there's still some contamination there, but it's much reduced. This little red X is an actual well. It's this well 19A, which is about 1,100 feet down gradient from the source area. And so this is actual data, observed data, and where we did the thermal treatments, and then we implemented the pump and treat, the revised design for pump and treat source control. And we're starting to see, actually, in the first 5 years, we start to see that decline from those two actions. And so we expect that to continue and have about this 30 to 40 year lifetime. So as a summary of all this, really the thermal treatment really significantly diminished the source. That was key. They did some excavation and removal of drums, and then the thermal treatment, and that was really a key element. We quantified pre and post treatment mass flux, and that really provided the data to assess how well that performed. And as you saw, it did a great job, greater than 98% decrease in the mass flux. And this approach also provides information for treatment design and site management. If you understand where the mass flux is, where's the hot spot, that's really going to help you design your treatment system and manage the site. And the passive flux meters were really important as part of that to get that mass flux data, as well as the Darcy flux on the flow. So we still needed pump and treat for source control because there was residual TCE. Again, Mike talked about that one lobe. So the thermal treatment got to specific areas, but there's still some residual TCE that had to be controlled. And we updated the design to better control that source area. And you see that we're really doing a lot better job of protecting the migration to the west seasonally and just controlling flux down gradient. And again, use the dogleg design in this system here. And again, the data indicate that performance is favorable. We're starting to see that detachment, and we're capturing most of the contamination in that PW1 through PW5. So in terms of impact and broader application, so you have to recognize your conceptual site model is going to evolve over time as you get additional data. The complex sites often require lots of characterization to really understand what's happening. Here we've got the seasonal variations in hydraulic conditions. We've got the two different aquifers with this window in between. A lot of things going on here. So we have to be able to adapt our management of the site to fit those complex conditions. And mass flux, it's really useful again for understanding the source strength at a site, how you design the source treatment, source control, and how do you assess remedy performance so that you know that you're having appropriate effect. So source control is really a key to minimizing this overall remedy duration. If we cut off the source, that means the down gradient I5 pump and treat and the lower aquifer pump and treat systems, they aren't going to have to keep running forever. They will have a finite reduced time lifetime. So these kind of approaches and tools can really apply at a lot of different sites. It doesn't have to be overly complex, but you can take these kind of approaches with the mass flux and assessing source control and different kinds of pump and treat. And we've actually put out PNNL and the Corps of Engineers put together a guidance document on pump and treat that talks about this, and it has a structured decision logic approach to address pump and treat. And how do you know when you're done with pump and treat? And then the passive flux meters, we've got the Hatfield article from 2004. It's a good reference for that. So here's just flash up. Here's some of the references. So you can come back to the video later and take a look at those if you'd like. And other than that, we'll say thank you for listening. And we'll be happy to take any questions you have.
Thank you very much, Mike and Chris, for your presentation. That was great, interesting project. While we have plenty of time for questions and discussion, and while people are thinking about that, posing their questions, please put them in the chat, and we'll go through them. But I do want to remind folks, because I know people start having to slip away for other work today. As I mentioned earlier, we have our next seminar planned for late April, and we'll be talking about climate change and climate resiliency and how you plan for that and factor that into remediation design and implementation. So Nick, I'm going to turn it over to you. What's that, Chris?
I'm just going to point out, we talk about the seasonal hydraulic changes. If the climate changes, those seasonal changes could vary. And so we might have to go and adapt this yet further. So.
Yeah, do you want to, okay, that's our first question to the speaker. Chris, do you want to elaborate? You and Mike want to elaborate on that? Not just necessarily the conceptual model, but also the understanding of how these things will behave, how TCE will behave in a different environment. Will it behave the same way?
With climate changes, you mean?
Yeah, with
So TCE, yes. I mean, it's the migration is going to be driven by the hydraulics, right? This particular site in these washes and tills, there's not a lot of sorption, not a lot of natural attenuation going on, at least microbial reactive natural attenuation. So I think that the TCE is going to do what it does, but the hydraulic conditions, when those change, yes, you may have to go back and do another update or revision to your source control in particular.
Just a quick thought on that. We have a new project starting out soon looking at the saltwater intrusion into coastal aquifer systems and the effects of both sea level rise and changes in precip patterns lead to increased salinity in certain regions. And there's some of these sites that were set up for bioremediation, which is supposed to take place for a long period of time. And all of a sudden the salinity changes and you got to reevaluate. So.
Well, those are both great plugs for why we picked this topic for our next seminar. So thanks for helping support that. Nick, I'll turn it over to you.
Yeah, definitely. And this idea of mixing the saline water with the existing water, it's such a powerful one. And the climate change is making that issue much more evident. And there are so many applications around the globe that, are very interested in that area. So that will be something that we definitely will consider in our next series of, at least the next seminar that is scheduled for the April timeframe, as Karen actually said. So we do have a question here, and Melissa Perdew is asking it. I'm not a scientist, but I'm wondering about the stakeholder engagement with the community for this particular project. And I think this is kind of an important question, especially for this project related to the work that you guys are doing in the Joint Base Lewis-McChord.
Yeah, so I don't, stakeholder engagement wasn't my focus, but it was definitely important because I have to go back a few slides here. If we see one of those pictures, let's use this one here. Right here. So you can see the objective was to keep contamination on post. And there's the city of DuPont right next door and American Lake here. So definitely it's important to have conversations and in the pictures that show the sea level aquifer, right? The TCE contamination goes through the window and then heads off to the west because the flow conditions are for that lower aquifer are different. And it actually heads around American Lake and there's a city well, water well that is down gradient. So that needs to be protected. So those are really key elements of the remedy assessment of how, how do we implement this holistically with the 3 different pump and treat systems and the source area treatment to maintain our objective of keeping contamination on post, right? So right. Like many sites, you discover the contamination in the groundwater many years after it's originally occurred. So there is, oftentimes things might have migrated off site, but how do you implement that to control that migration for the future? So those are key elements, and it's important to communicate that with the community that, here's what we're doing, here's how we're protecting your groundwater.
So one other thing I'll mention on that site was that EPA was very involved, Kira Lynch in particular, and very interested in innovative approaches to looking at complex sites. And I think through EPA, the link with the communities was stronger on this site maybe than many of them. So.
Yeah, all right. Well, thanks for addressing that question. I do have another question for you guys. Does Joint Base Lewis-McChord have enough data to do a meaningful mass balance assessment? And I know that you touched a little bit about that on the mass balance, but this is another question that we have for you.
I mentioned in there that we were pretty interested in the site right away because it was so well characterized, particularly the source area. I haven't seen that many sites with highly detailed characterization. Of course, they did that because they wanted to do the thermal remediation on the site. But the other thing is that when you look at the plume itself, I feel like it has more data than most sites have been involved with, and the extent of the plume, the width of the plume, the vertical dimensions, the link to the Vashon aquifer. I don't feel like there's that many sites that have that level of data. So one of the things I feel like is that someone needs to pull all that data together and put it into a mass flux and mass discharge framework, and maybe answer that question as to, okay, what are some of the uncertainties on these values? Do they still tell us what we need to know to understand the site? So just got to find a good graduate student for that. So keep looking.
Thanks, Mike. Unless Chris has anything else to add on that question, I do have another question for you. Go ahead, Chris.
No, that's fine. Go ahead.
Okay, and this is more has to do with a little bit with the work that we are doing here at Hanford as well, where we are trying to test different technologies. And I was wondering whether there are other remediation technologies aside the pump and treat that were considered for the source thermal or treatment of a down gradient plume. I just wanted to know the answer to that.
Yeah, there's a couple of things. So there was a remedial alternatives assessment that was done as particularly related to the sea level aquifer, this lower aquifer here. So we looked at bioremediation, and I think we looked at it at up gradient of this window to cut off the TCE migration down through the window to the lower aquifer. So I think it was looked at as essentially a PRB of bioremediation. We also looked at zero valent iron as a PRB in that area. And then along with the source control options. And then I guess another one was the actual pump and treat in the sea level aquifer here. We did look at a variety of options. It turns out that the pump and treat in the lower aquifer was the most cost effective and best in terms of cost and performance, did what we needed it to do, better than the ZVI and bioremediation.
One other note on that, I recall that there was a study of injection of whey, like cheese whey material to stimulate microbial degradation. There was also low temperature heating that was also aimed at microbial. Those are both for the source area. And
right.
They never got implemented at full scale, but at pilot scale, but at least there was some consideration. Yeah,
there was also another, I think they were probably all ESTCP demonstrations. Yeah. And there was another one with ZVI and shear thinning fluid in the source area to look at those different technologies and see how effective they'd be.
And all this data are documented in the one of the documents that you presented at the end as sources of support for this presentation, correct, Chris?
Right.
Yeah, that would be great. Okay. And there is another question coming from Gui Wang, who is a scientist here at PNNL. And Karen, you said that we might be able to turn on the mic for people to ask directly the question. And I would like Gui to ask that directly if we can.
That would be great.
Can you hear me?
Yes, we can hear you, Gui. Yeah.
Oh, yeah. So I'm just wondering, you use the thermal treatment, and then after thermal treatment, you see the TCE signal rebound, because this is really popular from the pump and treat, and because of back diffusion. So you got rebound signal after the treatment, you stop it. Did the thermal one, and you didn't see the rebound.
Yeah, so Mike.
Yeah, our pre and post, we came back 15 years later, and I don't have the numbers, but the mass discharge, I think, was within like 20 or 30% of what it was. So there was not a significant mass rebound in the thermal areas. The other thing that supports that pretty nicely is that the pump and treat, both data that Chris showed and I showed, is declining with time, and asymptotically, of course, but there's really no evidence of a significant rebound from that.
Okay, I have another question. Okay, just see the slides. So 2003, you had a hot spot about 35 to 40 meters. And after treatment, you see the hot spot downgrade moving to about 5 meters. So what's the reason why they're moving to more depth below the surface?
I didn't quite get that last part.
Yeah, the right column, the hot spot is on the 35. And then the 2018, the hot spot is on the 5 meters. And it is
Yeah, that's a good question. I think that may be related to some of what Chris showed with groundwater flow directions changing on us. You know, I think over that long time frame, it's possible that the groundwater flow direction shifted a little bit, and we're seeing some flux, even though it's low in that part of the transect. That's possible, anyways.
Yeah, I forget exactly. You know, we did do some changes with the infiltration gallery and the pump and treat.
That's right. I forgot about that.
So those things can have an effect, as well as, you know, you look at the scale here. This goes up to 100. This is whatever, 16,000, right? So I think there's probably a combination of things that occur that make this the hot spot, the post-treatment hot spot, and hot being relative.
Yeah, that's right.
Okay, I do have one final question before I turn it over to Karen. Given the 40 years of source control, pump and treat is still a long time, are there any other plans to address the remaining source with active treatment?
Yeah, that's a good question. I think that fits into the adaptive management, and, you know, who knows what will happen with climate change and how that might affect things. But definitely there is residual TCE, and like Mike talked about, you know, there's spots where there's some NAPL still. But it's not. It's more distributed. You know, the NAPL areas that were treated with thermal were pretty focused, high concentrations. Clearly target NAPL zones to treat, but there's other residual NAPL that if we wanted to reduce that nominal 40-year lifetime, yeah, we should go out and treat that. We have looked at, the Corps of Engineers and PNNL looked at approaches to do some bioremediation. You know, we've had these various ESTCP demonstrations, but we did another modeling exercise to look at different design options for bioremediation, with the key constraint being the groundwater flow. If you're going to do bioremediation, you don't want everything to just kind of flow down gradient way too fast before it reacts. And so we looked at some options to implement some flow constraints in here so that bioremediation would be able to take place and let the microbes do their thing and eat up the residual TCE. that wasn't a priority. You know, Fort Lewis, Joint Base Lewis-McChord, and some other areas that are currently a priority, but definitely something like that could be implemented in the future to help the overall lifetime.
And if I may, there is another observation actually added here in the chat. And I don't know whether it's an observation or a question. Jen actually asked that the TCE flux ranges are very small in 2018. You guys have anything to say about it?
Yeah, Mike.
Yeah, I mean, we going into this, you know, would have argued that there's high potential for back diffusion. One thing we haven't talked much about is the till unit underneath this, and there were actually, we had some wells that went down below that till unit into another aquifer because there was concern about TCE down there and whether the thermal would mobilize DNAPL, and there are a lot of concerns about all of that. But all of those were low, much lower than what we saw in the upper outwash aquifer, and I don't feel like or see that there's strong evidence for like a back diffusion scenario off of the till, and this 10 well transect is I feel like a pretty good way to assess that. That could be what flux is left over as a result of that, but making that link probably requires maybe some new coring and something like that to know for sure what things look like at the interface between outwash and till. And I'll just follow up with what Chris said. The groundwater velocities here are quite high. Hydraulic conductivity is quite high, and that's good in one sense because things flush through. But you know, if you want to control it and maybe do bioremediation or the capture wells, flow directional changes, those become really difficult with the high groundwater flow velocities we have.
Yeah, well, good points. Well, thanks again for an outstanding presentation, and I'm sending it back to Karen.
Yes, thank you, Mike and Chris, for the work you put in to prepare this and the time you spent with us today. We really appreciate it. Thanks to all our participants. Thanks to Kelly McIntosh behind the scenes for hosting our meeting. And I've put our email address in the chat. If you want to join our mailing list, please send us an email request. I've also put in our LinkedIn link and a link to a survey. So we appreciate everybody's time today, and we look forward to seeing you again in April. Thank you.